Hi guys, so today is the last day of new stuff for this unit. What we're going to do is look at a type of graph that's really going to combine all of the graphs you kind of have learned so far. And we're going to use something called a piecewise function. So what a piecewise function is, it's really just little pieces of different graphs with different domains. So to start, we're going to look at what both the graph looks like and what the equation looks like. So a piecewise equation looks something like this. So what you have is you have one equation with its own domain, another equation with its own domain, and you could have as little as two, as many as you want. In this case, I've got three. That's not how many you have to have, but this is just what we have on our example. So to start, we're just going to evaluate some points and understand kind of how the domain on here works. So I'm going to start by evaluating f of negative 4. Well, f of negative 4, when x is negative 4, I need to look at my domains. And I need to figure out which domain is negative 4 actually a part of. Well, that's this first domain, when x is less than negative 2. So if I plug in negative 4 to the original, I get negative 8. And I only plug it into that first one, because the other domains don't actually include the x value of negative 4. All right, let's go to the next one, f of negative 2, when x is negative 2. Well, negative 2 is on there twice, but it only equals negative 2 in one equation. So in this case, we're using the middle equation. The middle equation doesn't even have an x. My value is just 4. All right, going into the last one, or the next one, f of 0. Okay, 0 is going to fall in that middle domain, which means the equation I'm using is y equals 4. All right, f of 3. f of 3 is going to fall in the last domain because that's where it's or equal to. So I would do negative 3 times 3 minus 7, which should be a negative 16. And then finally, f of 5. So the x value of 5 is going to fall in the last domain. So I would plug in 5 to the last domain. Negative 15 minus 7 is a negative 22. So now we'll look at a graph. So this graph over here is an example of what a piecewise graph can look like. Now they can look like all sorts of different things. They don't have to look like this, but you see how it's little bits and pieces here and there, starting and stopping. So we're just going to evaluate some points in this graph. Really, this is something you guys have already done before. Okay, f of negative 1, when x is negative 1, your y value is 0. f of 2, when x is 2, your y value is 1. f of 1. Now there's two circles there. The filled in circle is the actual value. f of negative 2, again, the filled in circle is the actual value. f of 0 is 1. So what we're going to do is we're going to go ahead and actually get some practice drawing these. So again, what we're going to draw the graph 2x minus 1 everywhere where x is less than or equal to negative 1. So there's a couple different ways you can do this. If you want to just graph the line 2x minus 1, that's not 2, and then just erase it until it's from this point on, go ahead. Okay, that's one way you can do this. The other option, what I like to do is I like to take my endpoints and plug in my endpoints to kind of know where I'm starting and stopping. Just because once we get past linear and we get into some of our other functions later on, it makes it a little bit easier. So let's go ahead and do it that way. So if I take negative 1 and plug it in, that gives me 2 times negative 1 minus 1. I get the point negative 1 comma negative 3, which is the point we had also the other way. That will be a filled in circle because it was or equal to. Then I'm graphing everything to the left of that point, which has a slope of 2. All right, let's go on to our next one. Again, if you want to just graph the line negative x plus 3 and then just stop kind of at that point, you can. Just keep in mind you do need an open circle at the end point because it's not or equal to. So if I plug in 1, I get 2. So the point 1, 2 is an endpoint for this graph. It is an open circle. Oh, sorry, that was the graph I just showed you a second ago. I thought it was negative 1, it's positive 1. Sorry about that. So there's 1, 2. I've put an open circle. I'm graphing everything greater, so everything to the right has a slope of negative 1. All right, looking at my next one. Again, how you choose to do it's up to you. I'm going to go ahead and plug in that negative 2 endpoint. So 1/2 times negative 2 is negative 1. So -2, -1 is going to be an open circle. Everything to the left of that point has a slope of 1/2. All right, let's go to our next one. This one has 2 endpoints. All right, so the line is just negative y equals -1. It's just a horizontal line, constant function. So -2, -1 is going to be a filled in circle. And what you'll notice, we already have an open circle there. That's okay. If that happens, basically it's going to become a filled in circle. You don't need to worry about the fact that that was open at one point. It is now filled in. Basically, your function is now continuous at that point. And we're going to continue until 3. At that point, we have an open circle. All right, now let's go on to our last one. Let's plug in that endpoint. That gives me the x value is 3. -6 plus 3 is a -3. So 3, -3 is going to be a filled in circle. The slope is negative. And that's my graph. So again, if you have a filled in circle where an open circle is, that's okay. That filled in circle will take precedent and basically fill in that spot. All right, so this is another piecewise function. The setup here is a little bit different, okay? So what we have, it says that I have f of x equals x minus 2 everywhere except where x equals -1. So when I have the line x minus 2 here, slope is 1. So let's go ahead and go, whoops, that's the one point we don't have. Here, 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 all of these points is the line x minus 2. The only place it's not is here. So let's say this graph did go through -1. Then -1, -3, that's the point that we're skipping. So what I'm going to do is I'm going to put an open circle at -1, -3. What I just graphed there, what's different from those previous graphs, that's an example of that removable discontinuity. So because both sides of the graph are still approaching that circle. So the other graphs, it kind of, like I said, it kind of jumped. Those were those breaks or jumps. But this one actually is a removable discontinuity. Now let's look at this last point here. When x does equal -1, y equals 3. So that's just a little point right up there. Now again, the reason this is removable, let's say this was -3. Well then, that whole graph would be continuous. All right, if you feel comfortable, pause the video, try this last one on your own. All right, so go ahead and plug in that first endpoint. So 1/3 times -3 plus 2. That's going to be -1 plus 2. So this is going to be -3, 1. And that's going to be a filled in circle. Everything to the left has a slope of 1/3. So it's going to go off my graph a little bit, but that's okay. All right, let's go to my next equation. I'll plug in both endpoints. So if I plug in -3, that would be +3 minus 2, so -3, 1. That's going to be an open circle. But again, as you notice, there's already a point there. That's okay. So I don't need to show the open circle. The other endpoint, if I plug in 0, 0 minus 2 is -2. So 0, -2, that is going to be an open circle. And then connecting those points, it's a slope of -1, which is true. That's what we have in our graph. That's what we have in our equation. Then our last one is a quadratic. So if I plug in 0 to get that endpoint, I get 0, -2. And again, there's already a point there, but we're just going to fill it in. So this whole piecewise function actually is continuous. And actually, I lied to you. It's not continuous because I did not make that or equal to. I left it as greater than, not greater than or equal to. So there is still an open circle at that point. All right, so this graph's going to have an open circle there. Everything to the right is the quadratic x squared minus 2. So if you don't remember what quadratics look like, pick some more points, plug them in. If I plug in 1, 1 squared minus 2 is -1. If I plug in 2, 2 squared minus 2 is 2. And I can get some more points that way if you don't remember the shape of that parabola. right, so now we're going to go backwards. We're going to go ahead and write the equation from the graph. So this, again, really not that hard. Pretty good review for domain, honestly. So let's start with the first one. We're going to start by writing the equation of the first graph. So I'm going to write the equation of this line. So again, we need the slope and the y-intercept. This has a slope of -1/2 and a y-intercept of 1. So then we also include the domain. Well, it's everything less than the point 2. Again, open circle there, so we're using not or equal to. Then we write the equation of the second graph. So we'll find the slope. That has a slope of 1. And then I need the y-intercept. So if it's a pretty easy point like this, let's just continue it and see what the y-intercept is. It's probably the easiest way. Some of these you will need to go back and solve algebraically, but this one's pretty simple. And then I include my domain. All right, looking at the next one. So the first graph on there is just the line y equals 3. That domain is x is less than -1. Second graph, that's a parabola. That parabola has been shifted up 1. So that equation is x squared plus 1. The domain, it's from -1 to 2. The -1 is included with a filled in circle, so it needs to be or equal to. Then we get to the last one, write the equation of that line. The slope is -1. We can't see the y-intercept, but I'm just going to continue it, and I can see that the y-intercept is 4. Write my domain, and I end up with the domain of x is greater than or equal to 2. All right, if you're writing the equation of a piecewise function, and you have kind of an overlap like this, then you don't need to stress about which one has the or equal to. You can put it in either place and it's going to be okay. Now, I know a lot of you guys are probably looking at this and realizing, hey, this is just an absolute value graph. Yes, it is, but I want to get some practice on writing linear functions and finding intercepts for linear functions. So we're going to write this as a piecewise equation of 2 linear functions. So let's start with our first line. All right, so this one, we need to find our slope. So let's find 2 pretty points. So I've got one here, and I got one at the vertex. So that's going to help me find my slope. So I've got a rise of 1, 2, 3, 4. And then I've got over 3. So that is a -4/3 slope. But if I were to continue this graph, I'm not going to get a pretty y-intercept. So I'm going to need to solve algebraically in order to find what that y-intercept is. So you got a couple different ways you can do this. One is you can use point slope formula and just get it in y-intercept form. And that's probably how I'm going to do it. So point slope form, y minus y1 equals mx minus x1. You can use either point. You can use the top point or the vertex. So I'll go ahead and use that top point up there. So I've got y minus 5 equals -4/3 x plus 8. So y minus 5 is equal to -4/3 x minus 32/3. So y is equal to -4/3 x minus 32/3 plus 15/3. So I end up with -4/3 x minus 17/3. So again, kind of an ugly y-intercept, but just really kind of trying to review some of that algebra 1 here. All right, let's go ahead and do the right part of this graph and our domain. So again, where the or equal to goes is up to you. I can make this x is less than -5, and I can make the next one x is greater than or equal to -5. It doesn't matter where the or equal to is as long as it's on one of them. All right, so on the next one, again, let's find a good point. That's going to be a 4/3 slope. But I don't know the y-intercept, so we're going to solve for it algebraically. I'll use the vertex this time. So y minus 1 equals 4/3 x plus 5. I'm going to add that 1 to the other side, and I get 4/3 x plus 23/3. over 3. So what we're going to do now is we're going to solve this absolute value, or write this absolute value equation as a piecewise function. But instead of looking at the graph, we're just going to do it based off the equation. Now, if you want to go ahead and graph this and do it the same way, you're welcome to do that. But what I want to do is kind of show how we can get this just using kind of our point slope form and some stuff from Algebra 1. So what we know about this absolute value function, all right, we know that it's going to open down. We know that from the vertex, it would have a slope of either positive or negative 3. We know the vertex is going to be at 2, 4 because this graph has shifted right 2 and up 4. So we know we're going to have 2 lines. Well, I'm going to write these lines in point slope form. But to make it a little bit easier, because I already have f of x by itself, I'm going to go ahead and get y by itself and go ahead and move that y1 to the other side. So we know these two equations, again, they're both going to go through the point 2, 4 because that's the vertex. One of them is going to have a positive slope, and one of them is going to have a negative slope. Where it's going to change between the two is at the vertex. The x-coordinate of the vertex is 2. Now, because this graph opens down, everything to the left is when it's going to be at the positive slope. So this is going to happen when x is less than 2. Because the graph opens down, everything to the right is the negative slope, so that's happening when x is greater than 2. One of these needs to be the or equal to. It doesn't matter which one. I'll go ahead and make the top one the or equal to. And then I'm just going to simplify it. So I'll rewrite this as 3x, so that's minus 6 plus 4. This would be negative 3x plus 6 plus 4. And that's my absolute value equation. All right, so when we talk about piecewise functions, intersections get a little bit different and a little bit harder for us because they include an extra step. So normally intersections, we're just solving a simple equation. And that really is what we're doing here. The problem is this graph could potentially intersect in 3 places. It could intersect nowhere because the domain comes into play. So what we need to do is we need to consider each possible case. So let's look at the first case. If the line 1/3 x intersects with 3x plus 7, we know they do, we just need to find out where. So 3x plus 7 is equal to 1/3 x. So let's go ahead and solve this out. So that's going to give me 8/3 x is equal to negative 7. So x is going to equal a negative 21 over 8. So I know where those two lines are going to intersect. I need to consider now, is that intersection point in the domain of that graph? Well, negative 21 over 8 is less than negative 2, so yes, that one is true. Well, now let's see, hey, this could intersect with the middle, so because the middle is a completely different graph. So let's try the middle one. So negative 2x plus 1 equals 1/3 x. Well, let's go ahead and solve this out. So I get 1 is equal to 7/3 x. So x is equal to 3 over 7. I need to consider, does 3 over 7 fall in this domain? And yes, it does. It's less than 1 and greater than negative 2. All right, now let's try the next one. Negative 1/2 x minus 1 is equal to 1/3 x. So negative 1 is equal to, I need a common denominator, add those two fractions together, and that's going to be 5/6. I've got 2/6 plus 3/6. So I get that x is equal to a negative 6 over 5. Well, is negative 6 over 5 in the domain x is greater than 1? And no, it's not. So that is not an intersection point. So if you were to actually graph this, you would find 2 intersections. You would find where it does intersect the first 2 parts, it does not intersect the last part. All right, so the last thing we're going to look at that's really helpful for piecewise function is word problems, because there are some applications where you're not going to have the same function for the entire domain. So let's consider this one. So at City College, tuition rates for in-state residents were $92 per credit for the first 10 credits, $35 for credits 11 through 18, $74 for credits over 18. So we're going to write this piecewise function. So for the total tuition. So the total tuition based on the number of credits. So let's start with the first equation. That's the simplest. $92 a credit for the first 2 credits. Well, that one's pretty easy. 92 times C, as long as C is less than or equal to 10. But we also need to consider, though, it can't be negative. We're not going to have a negative number of credits. All right, now let's try the next one, credits 11 through 18. Well, the domain's pretty easy here. Okay, my domain is going to be 11 is less than or equal to C is less than or equal to 18. All right, we know those credits are going to be $35 per credit. So it gets a lot cheaper in that section. So I know that that's going to be 35 times the number of credits between 11 and 18. But be careful here. I can't just say 35C. Because if I did 35C and there's 11 credits, that's saying all 11 credits are $35. That's not the case. The first 10 cost us $92. So this is only 35 times the credits over 10. What I also have to consider, if I leave it like this, that's good. That's telling me how much, if I plug in 11, that's going to tell me how much my 11th credit costs. If I plug in 18, that's going to tell me how much the credits 11 through 18 cost. But our function is based off of the total tuition. The total tuition is all of our credits, which includes the first 10 hours that we already got. Well, if I have 12 credits, I've obviously gone past 10, so I have to include the full price of 10 credits at $92 per credit as well. All right, then looking at the last one, it's going to be $74 per credit over 18. So I can say C is greater than 18. I could say it's greater than or equal to 19 if you wanted to show those whole numbers. I'm just going to say greater than 18 just because that's how it's written. Because again, we're not going to have partial half credits here. It's only going to be those discrete values. All right, so looking at this last equation, again, $74 per credit, so I know it's 74 times C. But again, it's not all of the credits, it's all of the credits past 18. And then since we're not just finding the individual credit cost, we're finding the total tuition, I need to consider, if I've gotten to 18 credits, I've gotten past 10 credits. I've also gotten all the way through 18. So I need to consider, hey, how much would it cost for me to get that full 18 credits? So I wrote it as plus 920, and then I can do plus 35 times 8. Or I'm just going to go ahead and erase it, and I'm going to go back and plug in 18 basically to my original equation. So 35 times 8 is going to be 280. 280 plus 920 is 1,200. So if I've gotten to 18 credit hours, I've already spent $1,200 on the first 18 credits. Now every credit I go past that is going to be $74. All right, so that is it for piecewise functions and for Unit 1. So Unit 2, we're going to transition in kind of a different unit. We're going to look a lot at systems and matrices. So a little bit off our normal kind of Algebra 2 pattern with functions, but we'll pick it back up kind of after that unit with normal functions.